Okay, so we now have our conformal Killing vector. So let's try to analyze it. So first of all, we're going to think about this parameter A alpha. And we briefly mentioned that A alpha corresponds to translations. So let's dig into this a little bit more. Well, what would our transformation be here? So I'm going to set zeta alpha equal to A alpha. So I've set all of the other parameters to 0. This is the transformation that we're considering. And then you can see that x tilde alpha is equal to x alpha, and we are adding a constant. Well, that's obviously a translation. Okay, as we said before, A alphas are parameters of translations. How many parameters are there? Well, there's a total of d parameters because the alpha index runs over d values. Another thing that is interesting to ask is, what is the dimension of A alpha? Well, we know zeta alpha gets added to x. X is a length, so zeta alpha itself has to be a length, and that means that A alpha also has to be a length. So the A alphas, the parameters of the transformations, are actually lengths. So far, we've considered an infinitesimal transformation. So now let's take a look at the form of the finite transformation. And well, it's very easy. Um, x tilde alpha will be equal to x alpha plus A alpha. So the only difference to the equation that we were writing down previously is that now A alpha is finite. Okay, so this is finite. Previously, when we wrote equations like this, the A alpha is infinitesimal. But otherwise, the form of the transformation looks exactly the same. This is special to translations. It's not going to be the case for any other transformations that we look at. Translations are particularly simple. Now let's ask ourselves, what is the generator? Well, so that any translation by a finite parameter A, if we act on x alpha, we know the form of the transformation. It'll just be x alpha plus A alpha. And because we're dealing with a Lie group, we know that this can be written as e to the I x alpha, sorry, e to the I parameter of the transformation. So A alpha and then P alpha acting on, let's call it, let me change this index here. I don't want to give more than one index the same name, so let me make it A beta, P beta, and we'll act on X alpha. So that's the finite form of the transformation. And then, as we said, to get the generator, we should consider an infinitesimal transformation. And so let's just write this all down for an infinitesimal transformation plus A alpha. And this will be e to the I A beta B beta X alpha. And remember that we can expand this out because we can ignore order alpha squared. So this is just 1 plus I A beta P beta acting on X alpha. Now we compare the two sides. So this X alpha is reproduced by this 1 times X alpha. And that tells us this A alpha has to be reproduced by the I A beta P beta acting on X alpha. So we've got A alpha must now be equal to I A beta P beta X alpha. And exactly as before, the equation that we want to use is that d beta on X alpha is delta alpha beta. So using that equation, it is very, very easy to verify that P beta is minus I d beta. So maybe just writing things out once in detail, it's minus I d by dx beta. So that is the generator of translations. We have the first element of our Lie algebra. Great. Okay, so that was translations, very easy. Now let's move on to Lorentz transformations. So let's look at omega, alpha, beta. Okay, and so again, we'll set everything else to 0. First thing to note, we know that omega is antisymmetric. That means if you were to count how many parameters there are, there must be d times d minus 1 over 2 parameters. Because it's antisymmetric, alpha and beta must be different. So alpha can be any one of d, beta any one of d minus 1. And then because it's antisymmetric, omega alpha beta is the same, well, up to a sign as omega beta alpha. So we need to divide by 2. The infinitesimal form of the transformation is zeta alpha is equal to omega alpha beta x beta. So from this equation over here, we can now work out what are the dimensions of omega alpha beta. Now remember, the conformal Killing vector is a length, and x beta is also a length. Well, that tells us that omega alpha beta must be dimensionless. Now this makes sense because when we think about what omega alpha beta is, omega alpha beta are the parameters of a Lorentz transformation. That means that they are either angles of a boost, angles of dimensionless, angles of a rotation, angles of dimensionless, or they could be rapidities of a boost. And rapidities are also dimensionless. Okay, let's just go through an example of a finite Lorentz transformation just to make sure that things mesh with what we found from our conformal Killing vector equation. So remember that in general, x tilde mu will be equal to a lambda mu nu x mu. And we're just going to work with one specific example now. So let's say we take x tilde naught, x tilde 1, x tilde 2, x tilde 3. So this is our x tilde mu is equal to, and I'm going to consider a boost along the x direction. So this is one Lorentz transformation that we studied an awful lot last year. So I'm hoping that it is familiar to you. And if you haven't seen this before, why don't you check that this is a Lorentz transformation? So you should check that this leaves the Minkowski metric invariant. And then we've got x0, x1, x2, x3. And to make contact with our discussion so far, we now want to let phi be infinitesimal. So let phi be infinitesimal. And if we do that, then the cosh of phi, this is equal to 1. There's actually an order phi squared correction to this equation, but we don't care about phi squared because phi is infinitesimal. And the sinh phi will be equal to phi, and there'll be an order phi cubed correction, which again we don't care about because phi is infinitesimal. So if we use these infinitesimal results for cosh phi and sinh phi, we can now just multiply out the matrix, and what do we get? We get, actually, let me just move this slightly further down. We get x tilde naught is equal to cosh phi x naught, so that'll just be x naught, and then we'll get plus sinh phi x1, so this will be plus phi x1. We will have x tilde 1 will be equal to, it'll be x1 from the cosh phi, and then it'll be plus phi x naught. X tilde 2 will just be x2, and x tilde 3 will be x3. Now, how did we write our omega? The thing I want you to pay attention to, on this side of the equation, the index on the killing vector is up, but on this side of the equation, the index on x is down. So I want to put all of these x indices down. And the way that I'm going to do that, so I again have to say what metric I'm working with. So I'm going to say I'm working with this metric. So it's the Minkowski metric we always know is diagonal. So I'll just tell you what are the diagonal elements. And I think going with what we said in 2 dimensions, I'm going to choose 1, minus 1, minus 1, minus 1. If I'm using a slightly different convention and you don't like it, that's fine. You use your convention. We can use whichever convention we like. So from this, let me now just use this metric. This will be equal to x naught. If I lower the 1, it'll cost me a sign, minus phi x1. This will look like x1. And if I lower the naught, it'll cost me nothing, because the first element on the diagonal in eta is a plus 1. So we can lower x naught, it'll cost us nothing. So we've got plus phi x naught. So from this, we can read off the parameters of the transformation. We've got omega naught 1 is equal to minus phi. Omega 1 naught is equal to phi. And all other values of omega vanish. So what you see, and this is the important thing that we checked, is that omega really is anti-symmetric. So this really is a Lorentz transformation. As we said, it should be omega alpha beta was meant to be anti-symmetric, and indeed it is. And you can check this is the case for all of the Lorentz transformations. Now let's work out what the generator looks like. So just like we did for translations, we're going to look at an infinitesimal transformation. So we've got T of omega. This is going to act on x alpha. And this we usually write as e to the I. Now here we've got an omega mu nu. And we've got the generator of Lorentz transformations, which is m mu nu. Now mu and nu are summed. So for example, I could have mu as naught and nu as 1, so omega naught 1, but I could also have mu as 1 and nu as naught, omega 1 naught. So we'll be summing omega naught 1 and omega 1 naught. But those two give us exactly the same transformation. So not to overcount, we usually include an extra factor of 2 there. And it's after including the extra factor of 2 that our parameters really correspond to rapidities and rotation angles. So it's useful to include that too. It's just a convention. It's just a choice. You don't have to do it, but we're going to do it. And then this would act on x to the alpha. And now we cash in on the fact that omega is infinitesimal, so we can expand the exponential, and we need only include the first term. This is omega mu nu over 2 m mu nu, and this acts on x alpha. Great. We will continue in a moment.